After studying this module, you shall be able to understand the basics of gelator, compounds responsible for gelator formation, application of gelators, basics, classification and application of fibers, basics, classification and application of adhesives. Gelators. Any substance capable of forming gel is termed as gelator. A gel is a soft, solid or a solid-like material that contains both solid and liquid components. The solid components are called as gelators. This is present as mesh network of aggregates which immobilize the liquid component. Dorothy Jordan Lloyd proposed in 1926 only one rule seems to hold for all the gels, that is that they must be built up from two components. One which is a liquid at temperature under the consideration, and the other which the gelling substance proper, often spoken of as gelator, is a solid. The gel itself has the mechanical properties of a solid, that is, it can maintain its form under stress of its own weight, and under any mechanical stress it shows the phenomena of strain. Gels can be classified in different ways based upon the chemical nature of components or physical state of bulk phase. In general, gels are classified as chemical gels and the physical gels. In chemical gels, the formation of cross-linked network occurs through the covalent bonding, whereas in case of the physical gels, the formation of a cross-linked network occurs through the non-covalent interactions. During the formation of gels, the organic molecules are involved as solid components. These are sometimes also called as organogelators. On basis of components, organogelators are classified as one-component organogelators and two-component organogelators. One-component organogelators. In one-component organogelators, a compound is present in a solution and forms a gel with the solvents. The gelator molecules are stacked one after one to form the gel network by the non-covalent interactions such as pi-pi stacking, hydrogen bonding, van der Waals interaction, etc. And hence comes under the physical gels. Different types of compounds given below have been used as one component organogelator. Anthracene derivatives. The compound 2,3-bis N-decyl oxyanthracene is a good organogelator and works at low concentration for a wide range of solvents ranging from alkanes to alcohols, ethers, ketones or halogenated molecules. The molecules of the structure 1 are self-associated by van der Waals interactions and dipolar force. This gelator also has ability to grow organically modified hybrid silica fibers. Another anthracene derivative 2,3-bis 9-decyl oxyanthraquinone as shown is also an efficient gelator of organic solvents. Steroidal benzene conjugates. The steroidal aromatic conjugate organogelators consist of an aromatic group linked to steroidal moiety through a suitable linking group. The compounds 3 and 4 possess a gelatian properties in the various organic solvents. Steroidal anthracene derivative conjugates. The cholesterol 4,2-ethyl oxybutyrate, also called as CAB, shown is a steroidal anthracene conjugates and gelate a wide range of solvents like alkanes, alcohols, aldehydes, carboxylic acid esters, amines and aromatic solvents. Another conjugate compound 6 also gives the gelatian properties with the organic solvents. The replacement of 2-enthryl power of the compound 6 by the other groups like phenanthryl, pyrenyl or 9-enthryl did not give the gelatin properties with the organic solvents. The driving force for the formation of the aggregates leading to the gelator molecule was due to the pi-pi stacking, van der Waals interaction and the other non-covalent interactions. Terpenoid benzene conjugates. A terpenoid benzene conjugate 7 is able to form gel with different alcoholic and mixed solvents. This compound gives stable and efficient gels with the aliphatic alcohols at less than 1 weight percentage of the gelator. Sugar-based organogelators. The sugar-based compounds also act as organogelators for organic solvents. The compounds 8 to 14, as can be seen from the figure, like methyl benzylidene monosaccharides, are very effective organogelators. They form aggregates with the solvent molecules through the formation of hydrogen bond. The formation of the hydrogen bond can be authenticated by FTIR and temperature-dependent NMR spectroscopy. The polar sugar parts can form a chain of intermolecular hydrogen bonds in organic solvents and exposes the aromatic parts to the solvent. Two-component organogelators. In two-component gelator system, one component can be present in isotropic solution and only on addition of second component a gel is actually formed. In this system, one compound forms a complex with another compound using donor-acceptor interaction, hydrogen bonding, etc. Different types of compounds have been used as two-component organogelators. Firstly, pyrene-based gelator. The pyrene derivative compounds 15 to 18 formed gel with different organic solvents in presence of trinitrofluorinone TNF due to charge transfer interaction between pyrene unit and TNF. The gels so formed have been found to be stable at room temperature for several days. Terpenoid-based component gelator. The derivative of natural products, arginolic acid, forms a thermo-reversible gel with organic solvents in presence of electron-deficient guests like picric acid. The change in color from yellow to deep red was observed during gelation. The charge transfer interaction between the aromatic part of a trypene derivative and picric acid has been observed and checked with the temperature-dependent UV visible spectroscopy. Application of gelators. The primary application of gelators are to form useful gels. Low molecular weight gelators are important and received more attention in comparison to the polymeric counterpart for a number of applications. This is due to their thermo-reversible nature and prompt response to external stimuli. A good gelator must show critical balance between hydrophilic and hydrophobic interactions in gelation process. The presence of an aromatic ring in a small molecule gelator is very helpful in inducing self-aggregation towards gelation. The aromatic moiety having planar nature favors pi-pi stacking interactions between the molecules involved and leads to the formation of three-dimensional networks of gels. The gels formed have wide application in different aspects of life, including electronic and photonic applications like organic electronics imaging, sensing application, etc. Fibres. The word fiber is derived from the Latin word fibra, which means a cylinder, elongated, thread-like object or a structure. In English and French, it is called fiber. It is defined as one of the delicate hair portions of the tissues of a plant or animal or other substances that have length 100 times its diameter. In general, it is a morphological term for a substance characterized by their flexibility, fineness, and high ratio of length to cross-sectional area. The history of fibers is as old as human civilization. The fibers have been utilized dates back to early Egyptian and Chinese, who used papyrus mats in the pyramids and the Buddhist temples to reinforce and consolidate the foundations. The utilization of silk in semi-technical applications also goes back in the history, where Mongolian armies wore silk next to their skin to reduce the penetration of incoming arrows. The use of silk in wound dressing and open cuts in web and fabric form also dates back to the early Chinese and Egyptian eras. The fibers have enormous applications to mankind since history to present day, and this will continue in future also. Fibers can be classified. They can be natural or synthetic. Natural fibers can be cellulose-based, mineral-based, or protein-based. Synthetic fibers can be organic or inorganic, wherein organic fibers can further be classified as natural polymer-based or synthetic polymer-based fibers. Natural fibers. Any fine hair-like substance that are obtained from any natural source are natural fibers. They are further grouped into three broad categories: cellulose-based fibers, mineral-based fibers, and protein-based fibers. Cellulose-based fibers. They are also sometimes called as plant fibers. They are extracted from plants and are also classified on the basis of part of the plant used. For example, cotton is cellulose-based fibers and obtained from seeds of the cotton plant. The cellulose-based fibers are also obtained from the stalk of plants like rice, maize, oat, wheat, etc. Jute is another example of this class. This is extracted from the bark of a white jute plant, Corchorus capsulurus, and is lesser extent from the Tossa jute, C. oletorius. Mineral-based fibers. The inclusion of the mineral-based fibers under natural fibers is conditional. They are not renewable and include clay-based silicates, asbestos form, etc. Usually, they are obtained by spinning or drawing molten minerals. Protein-based fibers. They are also called as animal fibers like silk and wool. The silk is obtained from the glands of insects, wool from hairy mammals, and avian fiber from birds. Synthetic fibers. The synthetic fibers are also called as man-made or chemical fibers. They are synthesized in the laboratories using chemicals. They are broadly classified into two types: organic fibers, which are synthesized from the petrochemicals based raw materials, which are polymerized into long linear fibers. They are further subdivided into the categories of natural and synthetic based polymers. Natural polymers. These are also called as regenerated fibers or semi-synthetic fibers. They are derived from naturally occurring polymers. For instance, rayon. It is made of same cellulose polymers that make up cotton, hemp, flax, and by structural fibers of wood. The rayon is obtained from cellulose by the reaction with sodium hydroxide and carbon disulfide and regeneration with the sulfuric acid. Synthetic polymer based. The synthetic polymer based fiber is a class of synthetic fiber. They are made up of polymers that do not occur naturally but instead are produced entirely in the chemical plant or laboratory. They are always obtained from the byproduct of a petroleum or natural gas. These polymers include nylon, polyethylene terephthalate, acrylics, polyurethanes, and polypropylene, etc. The first synthetic polymer-based fiber that appeared on the world market was nylon 66 in 1939. It was produced by DuPont and gained fast public popularity. The nylons are also referred to as polyamides, in which the amide linkage is a common factor. Another popular fiber, known as polyester, was also first introduced as Dacron by DuPont in 1951. This is today the second most used fiber after cotton and other synthetic fibers in terms of both production and consumption. The most popular polyester, polyethylene terephthalate (PET), which is also called as PET, is made by condensation polymerization of ethylene glycol and terephthalic acid. The product is further processed by melt extrusion and drawing. Polyacrylic fiber is a polyacrylonitrile and is a wool-like fiber produced by the polymerization of acrylonitrile. This is an addition polymer. They can spin into fibers by dry or wet spinning methods. Other addition polymers like polyolefin fibers such as polyethylene and polypropylene made from ethylene and propylene are also find their applications. Polyethylene has moderate physical properties with low melting temperature of about 110 degrees for its low density form and about 140 degrees centigrade for its high density form, which severely restricts its application in low temperature applications. Polypropylene has better mechanical properties and can withstand the temperature of up to 140 degrees centigrade before melting at about 170 degrees centigrade. Adipic acid and hexamethylene diamine combine together to form a polymer, nylon 66. Ethylene glycol and terephthalic acid undergo the condensation polymerization to form the polyethylene terephthalate. Inorganic or metallic fibers. The fiber which are produced from materials those are present in the Earth's crust and that are inorganic rather than polymeric in nature. Examples that are currently being used or considered as source of fiber are glass, metals, carbon asbestos and ceramics. The comparison of natural and synthetic fibers is summarized in the following table. The natural fibers are natural, whereas the synthetic fibers are completely man-made. If you look into the type of the two fibers, the natural fibers are staple or filament form, whereas the synthetic fibers are mostly filament form but sometimes cut into the staple form. Spinneret, there is no need for the spinneret in the natural fibers, whereas the synthetic fibers, it is essential for the filament production. Spinning process, not required with the natural fibers, whereas the synthetic fibers require that for the filament production. Chemical solution, not required for the yarn production in the natural fibers, whereas it is essential for the yarn production in the synthetic fibers. Very comfortable to wear are the natural fibers, whereas the synthetic fibers are not found to be so comfortable. Dust and impurities are present with the natural fibers, whereas they are absent in the synthetic fibers. Not possible to change the fiber structure of the natural fibers, whereas it is possible to bring about the changes in the synthetic fibers. The natural fibers grows with the natural color, whereas the artificial colors are added into the synthetic fibers. Natural crimp is present in the natural fibers, whereas crimp is implied on the filament in the case of the synthetic fibers. It is easy to dye the natural fibers, whereas it is not easy to dye the synthetic fibers. Natural fibers are mostly hydrophilic, whereas these synthetic fibers are mostly hydrophobic. Hair burn or the paper burn like smell is obtained when we burn the natural fibers, whereas it's a chemical smell when we burn the synthetic fibers. The production cost for the natural fibers is high, whereas it is comparatively low for the chemical fibers. Natural fibers are environmental friendly, whereas the synthetic fibers are not so environmental friendly. The durability, as far as is concerned, the natural fibers are less durable, whereas the synthetic fibers are more durable. There is a limited usage of the natural fibers, whereas the synthetic fibers are used for multitasking. Application of the fibers. Fibers have the utilities in all the walks of life. Few important and notable applications are: transport applications are an important end use area of fibers. The productions have their applications in tire, belt, safety belts and airbags. The fibers are utilized as technical textiles in industrial products such as filters, conveyor belts and abrasive belts, as well as reinforcement for printed circuit boards, seals and gaskets and other industrial equipment. The use of non-woven outweighs that of the woven and other fabric types. The consumption in 2000 is estimated at 70,000 tons and a little over 40,000 tons respectively. The fibers are also an important component for hygienic applications such as wipes, babies' diapers or nappies, and adult sanitary and incontinence products. Although attempts have been made to develop and introduce more efficient biodegradable fibers for such end users at low cost to avoid landfills and other environmental hazards. The fibers have its utility in household also. Hollow fibers with the excellent insulating properties are widely used in bedding and sleeping bags. The fibers has also been replaced the foams in furniture due to fire and other health hazards posed by such materials. The woven fabric are used in carpet and furniture backings and in some smaller, more specialized areas such as curtain header tapes. Nylon 6s is popular household carpet fiber. Polyethylene and polypropylene polymeric fiber have a density less than that of water, which allows them to float as ropes, nets and other similar applications. The availability, low cost and good resistance to acid and alkaline environments of polypropylene has greatly influenced its growth and substantial use in geotextile applications. The cloths and clothing components are the biggest consumers of the fibers. The category includes sewing threads, interlinings, waddings, insulation and the main outer and lining fabrics of the garment. The fibers find its applications in agriculture, horticulture and fishing also. These industries used fibers in the form of nets, ropes and lines and materials for covering, protection and containment applications. The fibers are also used for making temporary structures such as tents, marquees and awnings at the time of natural calamities. Adhesives. An adhesive is a material used for holding two surfaces together either by applying on one surface only or on both the surfaces. The basic definition of an adhesive is, as used by the Adhesive Sealant Council in America, is a material used for bonding that exhibits flow at time of application. According to Wu, adhesion refers to the state in which two dissimilar bodies are held together by intimate interfacial contact such that mechanical force or work can be transferred across the interface. The interfacial contact is usually arising from van der Waals forces, chemical bonding or electrostatic attractions. In today's life, adhesives are used everywhere, starting from postage stamped to highly technological manufacturing. The adhesives have taken the place of other joining processes like age-old bolts and welding and hence reduce the cost of manufacturing and labor. The major customers of adhesive companies are the construction sector, automotive manufacturers, aircraft manufacturers, and packaging industries. The adhesive industry is one of the largest in the world and comprising of the multi-billion-dollar industry. They can be used to join metals, ceramics, rubber, plastics, cork, and other combination of materials. If you look at the cross section of a bond, we see we have a substrate molecules which are binded together by adhesive. There are the boundary layers, surface of a substrate or an adhesion zone, a transition zone, and a cohesion zone. Some of the important requirements for a substance to act as an adhesive are: it must wet the surface on which it is applied, it must stick to the surface once applied, it must develop strength after it has been applied, and it should remain stable. The joining of the two materials using adhesive has some advantages and disadvantages. Advantages of using adhesive: they join thick or thin materials, similar or dissimilar materials, or in shape. Leads to uniform distribution of stress and larger stress bearing areas. Reduce or prevent electrochemical corrosion. Make joints with smooth contours and protect against a variety of environmental factors. Insulate against heat transfer and electrical conductance. Reduce vibration and absorb shock. Have excellent strength weight ratio with quicker action. Disadvantages of using adhesive: proper choice of an adhesive is required for specific purposes. Surface preparation played significant role to obtain durable bonds. Long cure times needed, particularly when high cure temperatures are not used. Cleanliness is required for most adhesives. For initial fixing, holders are necessities. The process is temperature sensitive. Natural origin adhesives are susceptible to attack by bacteria, mold, rodents, etc. Classification of adhesives. Adhesives can be classified on the basis of many aspects as shown. On the basis of sources, they could be natural adhesives or the synthetic adhesives. Natural adhesives are based on the vegetable and animal based sources. The organic material like casein, blood, albumin, hide, bone, fish, starch, etc. and inorganic materials like sodium silicate acts as natural adhesives. Most of their applications are limited to paper, paperboard, foil and light wood. These adhesives have a long shelf life but low strength properties. Synthetic adhesives. These are the adhesives that are not natural, are basically synthetic. The adhesives like elastomeric, thermoplastic, thermosetting, alloys, structural adhesives are all synthetic in nature. On the basis of the chemical composition, they can be categorized as thermosetting adhesives and the thermoplastic adhesives. The adhesives that cannot be heated and melted after the initial cure are known as thermosetting adhesives. The curing takes place by chemical reactions at appropriate temperature depending on the type of adhesive. This type of adhesives require considerable pressure. Example of thermosetting adhesives are polyester, polyimide, urea formaldehyde, polybenzyimidazole, etc. Thermoplastic adhesives. These can be melted without significant change in their properties and do not cross-link during cure. They are single component system. Wood glues are thermoplastic emulsions. These are common household items. They harden by evaporation of water from an emulsion. Example of these types of adhesives are cellulose acetate, polyvinyl acetals, cellulose acetate butyrate, polyvinyl alcohol, etc. Elastomeric adhesives. These materials are polymeric in nature. They have better toughness and elongation. Most of these adhesives are solvent dispersions of water emulsions. They have relatively low bond strength but flexibility is excellent. Some Examples of the elastomeric adhesives are natural rubber, styrene butadiene rubber, polyisobutylene silicone, etc. Adhesive alloys. Adhesive alloys form a combination of resins of two different chemical groups chosen from the thermosetting, thermoplastic or elastomeric adhesives. In most of these adhesives, heat and pressure are required for curing. They are solvent-based dispersions. They are stronger over wider temperature ranges. Example of these adhesive alloys are epoxy phenolic, neoprene phenolic, epoxy sulfides, etc. On the basis of the function, the adhesives can be classified as structural adhesives, which are of high strength and performance. They hold structures together and capable of resisting high loads. Polyaromatics, polyester, and polyurethane are some examples of this type. Non-structural adhesives. Non-structural adhesives do not withstand the substantial loads. They are only hold materials in place. Examples include adhesives that fill gaps and rubber cements that can be cements that used to stick paper to paper in office applications. On the basis of the physical form, liquid adhesives, these exist in liquid state and applied by the means of mechanical spreaders. Paste adhesives, these adhesives are high viscosities and applied on the vertical surface with less tendency to sag or drip. An example is modified epoxy adhesive that has a superior strength in metallic and composite structures like BR95 paste adhesive. Tape and film adhesives. These adhesives lead to uniform thickness and offer the advantage of easy dispensing. These are available as pure sheets of adhesive or with the film or paper reinforcement. Powder or granule adhesives. These adhesives exist in either powder or small granules. They are heated or dissolved in a solvent to get converted to a liquid form and then further applied to the required surfaces. Application of adhesives. Application of adhesives depends upon the selection of the material, quality performance of the product and the economy involved. They have unlimited applications from household to big industries. Some of the most frequent applications of the adhesives are in small-scale industries like food products, related industries, toys or stationery items. Adhesives play an important role in packaging and processing. In large-scale industries, adhesives are used in assembling spare parts of machines, car paints or branding them with labels. In construction industries, adhesives are applied for uniform distribution of stress. In addition to this, for painting and furnishing and home decor, adhesives play an important role. They are used in households for various day-to-day applications from glue sticks, sellotape or gums. In paper industry, they are used in multi-wall bags, in paper bags, as book binding and case making, corrugated paper, etc. They are also used in gummed tapes or textiles. They are used in rubber gasket to steel bonding, paper to steel, etc. They are used in some applications of wood to wood bonds, metal to plywood bonds, metal to metal, metal to plastic bonding. They are used as dental cements. They are used in electrical tapes, sealing tapes, ceramic tile adhesives, flooring adhesives, pipe adhesives and pressure sensitive tapes, etc. They are used in formation of mica board and used in abrasives, making laminated safety glasses, brake linings, foundry industry, fire bonding, plywood. They are used in making hot melt adhesives and for flooring, paper lamination, flocking adhesive, etc. They are used for bonding stone chips as concrete, grains to form mortar for bricks, etc. They play an important role in medical device industry. Dear students, this module deals with gelators, fibers and adhesives. A gelator is a gel forming substance. On the basis of the components, organogelators can be classified as one component organogelator and two component organogelator. In one component organogelator, a compound is present in solution and forms gel with the solvents. The gelator molecules are stacked one after one to form the gel networks by non-covalent interactions such as pi-pi stacking, hydrogen bonding, van der Waals interactions, etc. Different types of compounds have been used as one component organogelator. For example, anthracene derivatives, steroidal benzene conjugates, steroidal anthracene derivatives conjugates, terpenoid benzene conjugates, sugar-based organogelators, etc. In two-component gelator system, one component can be present in isotropic solution. Only on addition of the second component, a gel is actually formed. Examples are pyrene-based gelator, terpenoid-based gelators. Fiber is defined as one of the delicate hair portions of the tissues of plants or animals or other substances that have length 100 times in diameter. Fibers are classified as natural fibers and synthetic fibers. Natural fibers are obtained from a natural source, whereas the synthetic fibers are also called as man-made or chemical fibers. They are synthesized in laboratories using chemicals. Fibers have the utilities in all walks of life. Few important and notable applications have been listed in the module. An adhesive is a material used for holding two surfaces together, either by applying on one surface only or on both the surfaces. Adhesives can be classified on the basis of many aspects, such as on the basis of source, chemical composition, function, or the basis of the physical forms. The application of the adhesives depend upon the selection of the materials, quality, performance of the product, and the economy involved. They have unlimited applications from household to big industries.